and that is fine. Now we have I. I now connects back to H, right? So that again gives you an index of 5, and we have an index of 3 for the parent, and that gives you basically our parent being connected using a back edge. So that is how we basically detect that there are cycles in this particular uh, ordering or in this particular graph. So does that make sense how we can check? And so given this information, would you be able to write a program that can detect cycles in a graph? If I ask you in a homework, let's say, write a program that detects a cycle in a graph, would you be able to write it without looking at, internet sources? So if you understand that, tell me how would I implement this particular data structure that takes in a node number and gives you the index of that particular node. Can an array suffice for this particular data structure? Instead of A, let's say that I have numbered those nodes and I just have it 0. So an array would be perfectly fine to store this particular set of nodes, right? I just represent all of those letters with respect to their numbers. So A becomes 0, B, C, D, E, F, G, H, I, J becomes 9, and so on, right? And that gives you all of those indices. C basically becomes 2, and so on. Okay. So that was topological sorting of a particular graph. And how we can use topological sorts to do two things. One is to figure out an ordering such that we now know what are the things that I need to do first. So let's say that there is no cycle, right? So let's take the old example. Let's say that there is no cycle. In this scenario, I now know which of the things I need to do first in order to be able to complete the things later. So for example, I need to wear a shirt first in order to wear a tie after that. So I need to complete the parent task that would then allow me to complete all the child tasks of that particular graph, right? That is one use case of a topological sort. The other use case is to figure out if there are cycles or not. But for that, we need something extra to reinsert the edges back and check if there is a particular back edge connecting to a parent node. Okay.
Dr. Bose, I have a question.
Mhm.
So in the slide number 15, when you showed us that there could be a back edge,
Mhm.
but it would not be a circular, like a circular graph, right?
Mhm.
How would the indices work in that case? Yeah,
What do you mean?
as you've shown us, the when it's sorted, you have indexes for E, B, A, H, G as 0, 1, 2, 3, 4, right?
Mhm.
How would it work in that non-circular graph? It's on slide 15, the one you just created.
Are you talking about this one? No, no, no. You're talking about this one, right? No, I think you're talking about this one. No? Wait, I might be missing something. Is this slide 15? No, that's not slide 15.
I'm talking about the slide 15 on the presentation. Yeah.
This one.
Yeah. So how would the
Okay.
indexes work here? Since
Okay.
if we have like a back edge, it would not work with the rule that you just said, right?
Yes, but see, this particular example was to show that this particular node is this particular edge is not actually a back edge, right? This particular edge is actually a forward edge that connects from E to F, right? So that is fine. So in this particular scenario, D would be index 0, E would be 1, F would be 2, A would be 3, B would be 4, C would be 5. In this particular scenario, we do not have a back edge. However, if let's say that we did have a back edge that connected from F back to D. Now that is a back edge, right? And that basically gives you a particular cycle. And in this scenario, D is still 0, E is still F, E is still 1. But now for F, when we are inserting back the edges for F, we see that there is a back edge that F's index is 2 and D's index is 0, and we see that there is a connection to a parent. And that is how we detect a cycle.
Could we have an edge between like A and D, let's say?
We can have an edge between A and D.
And then if you could remove the top edge, the big edge on the top.
Okay.
Yeah, and let's connect A and D.
So we have D here, and we have a connection. This one?
Yeah. So now how would the circular thing work now?
Yes,
Would it not work?
now it is not a back edge though.
Okay.
Right, because ABC has to now go in front of it because it's a forward edge.
Oh, okay, that makes sense. Thank you.
Right, exactly. Once you order your nodes in a topological order, you cannot have back edges among differently connected components. I mean, disjoint components. I mean, sort of disjoint component. I'm considering DEF and ABC as disjoint. And let's say I introduce the node A, edge AD, immediately DEF would be ordered as, I mean, not immediately, it would be evolving like that, but DEF would always have a post number that is lower than ABC or any nodes from ABC, because at least A, because DEF needs to be completed before A is completed. Right? Do you agree?
Yeah, I got it now. Thanks.
Perfect. Okay, so any questions about how we can figure out whether there is a cycle or not?
Yeah.
Yes.
So you're basically talking about you'd iterate through those in order from 0 to 9, and then you'd iterate through each of his edges, and then you'd go check to see if the pre-visit number was always less than
post-visit number. You don't even care about the post-visit number anymore, right? You don't even care about, because these are odd. So let me just write this as positions. Let's say that this, I'm going to revert back to nodes here. So this was J, and this was A. This was supposed to be C. Yes. So essentially, once we have performed DFS on our graph, we have this ordering of our nodes, and this is the order that we have: E, B, A, H, G, I, C, D, F, J. Let's say that we save this particular ordered set of nodes in an array. That array would have these indices, right? 0, 1, 2, 3, all the way to 9. Right. Now, we are going to traverse through our adjacency list and looking at every edge. The first edge that we will look at is the one at J, because that has the lowest post-visit number. We start at J and we see that there is a connection from J to C. That also means that there is a connection from the node 9 to node number 6. And that shows us that there is a back edge in this particular ordering, and that gives you a cycle.
Okay, so you'd have to go through, iterate through all their edges to see if that position was
yes.
less than your current position, and then that would indicate. Okay.
Yes. If it was not, then we are fine, right? F can go to J, that is fine. D can go to F, C can go to D, that is, all of those are fine. But the moment we see that something is connecting back to a particular graph, then we would have that particular ordering. However, although this looks like a back edge, we should remember that this also, I have drawn this as a back edge, but if you apply DFS on this particular graph, it would order this where DEF is going to be a child of A, right? And so that is not technically a back edge. This topological ordering allows you to have back edges that always mean that there is a cycle. Okay. So now let's look at another example for topological sorts as well. We have this graph, that is, A is connected to B, B is connected to E, E is connected to F, then C, then D, then back to B, right? So let's say that I have this particular ordering that goes from A to B, then B to, then we have A, B, C, D, E, F in this order. We have E to F, the cycle, then F goes back to C, then C goes to D, then D goes to B, and B goes to E. Now, all of these edges are correct, but is this a legitimate ordering of our graph? And more importantly, how many back edges would this graph have? But I'll come to that in a second. Is this a legitimate ordering of our graph? So let's look at how we can figure out if it's a legitimate ordering or not. We start from A, fine. Then we go to B, fine. Then we go to E, F, C, and then D. So in this particular sequence, we have D. If we start from A, we are going to stop at D, where D would be the node with the lowest post-visit number. That would mean that D would be the first element at the very right. In this scenario, we have F as the very last element. So that was not the case for this ordering. So can we figure out a way of traversing and starting at a particular node in this graph that would end up at F? Is there any node that I can start my DFS search that would end up at F, where F would have the lowest positive post-visit number? So we can start at C, we go to D, we go to B, we go to E, then we would go to F, then we would come back, and then we would have A, won't I? Taha? A would still be left. So A would have that is a nice way. So C to D, D to B, B to E, F, then F would have the lowest post-visit number, then E. But then in that scenario, B would have the third largest post-visit number, right? You are correct. If we start from C, we would reach F as the lowest post-visit number. Then we would come back to E, that is fine. But the next one will not be D, right, Taha? It would rather be B. Exactly. So again, even if we start at C, this particular ordering does not make sense, right? So if we actually apply our DFS to this particular graph, we would have this particular ordering where let's say we start at A, then we go to B, E, F, C, and D, and there is only one back edge in this scenario that connects back to B, right? So this has a cycle. So if we ordered this in this order, A, B, E, F, C, D, then if we applied our topological sort to detect cycles, then we would start with D, and we see that there is a connection back to a parent node, and that gives us that indication that there is a cycle. And in this entire graph, there is just one back edge, right? Okay. So that is fine, but now let's talk about, so that was topological sort and how we could detect cycles. The next thing that I'm going to talk about is figuring out the strongly connected components in a graph. So basically what I want is, I want this as my strongly connected component, and I want this as another one of my strongly connected component, right? So everyone remembers what a strongly connected component is. So a strongly connected component is any set of nodes where there is a path between these nodes such that I can reach any other node from this node. So if I start from E, I can reach B because there is a path. I can start from E, then F, C, D, B, I can reach B. From D, I can reach any other node in this component here. From F, again, I can reach any other node in this section here. So B, E, F, C, D is one strongly connected component, and A is another strongly connected component because I cannot reach A from B or D or things like that, right? Okay, so let's say that I do want to find out all the strongly connected components of this graph. Now, what would have, so I have this topological ordering of this graph. What would happen if I started my search at B? What are the set of nodes that I will get if I start my search from B? Would I get B, E, F, C, D? Or would I get A, B, E, F, C, D? So what I'm asking is, would I get